Hi, my name is Aaron Jacobs. I'm a senior programmer at Double Fine, and I'd like to talk to you all about portals. First, some quick background information about me. I've been at Double Fine for a little over 6 years, during which time I've helped ship Day of the Tentacle Remastered, Psychonauts in the Rhombus of Ruin, and most recently, Psychonauts 2. I have the role of systems programmer, which means my focus is usually on lower level systems of art games as opposed to direct gameplay. I spend a bit of my time working in engine code, though due to the relatively small number of programmers at the studio, I tend to hop around between different types of tasks, including working on our build system, assisting with some of our internal tools, and even doing some camera design work. Over the last 4.5 years or so, I've worked on Psychonauts 2. For anyone who is unfamiliar with the game, it follows Raz, a psychic 10-year-old boy, as he uncovers the old secrets of an international psychic spy organization that he interns at, the Psychonauts. The game is a third-person platformer with a heavy focus on characters, narrative, and humor. Most of the game's levels occur within the minds of its characters, which let the team create an interesting variety of settings and goals for the player. The mental worlds also let us play around with the laws of physics, since they don't necessarily need to apply within the context of someone's mind. One memorable example of this exists in the Milkman conspiracy level from the first Psychonauts game, with its twisting geometry and relative gravity. Early in development, we decided relative gravity should make a return in Psychonauts 2, but we were interested in toying with other aspects of space as well. During some brainstorming, the idea of using portals was suggested. The name Portal has become somewhat ubiquitous ever since the game with the same title came out in 2007, but just to be clear, when I say portal, I mean a window that joins two locations in space. Some examples from other games include Valve's Portal, Demruth's indie puzzle game Antichamber, and 1047 Games' recent first-person shooter Splitgate. Portals were an exciting concept for us for two main reasons. First, they would help thematically separate the mental worlds of the game from the real world. But more importantly, they have the power to create unexpected and memorable moments for the player, as anyone who has played Arcane's Prey can tell you. However, we knew from the beginning that they would be difficult to implement well. As I mentioned before, Double Fine has a relatively small programming team. For example, there are only 3 of us at the studio that have any amount of graphics programming experience. We knew that we wouldn't be able to dedicate a massive amount of engineering time to portals, so we generally opted for whatever solution was simplest to implement whenever we encountered problems. We also knew that the engine integrations would likely be a problem. As a studio, we try to stay as up-to-date with Epic's releases as possible, as each version tends to bring with it improvements to our tools and workflows. Psychonauts 2 started production on Unreal 4.11 and shipped on 4.26. Covering 15 versions of the engine. We understood that implementing portals would likely require modification of our engine's rendering code, so we did our best to separate our code from Epic's as much as possible. Nevertheless, some engine updates ended up being pretty painful to integrate. Performance was another troubling issue, as portals can be very expensive to render, both for the draw thread and the GPU. As announced during our crowdfunding campaign, we planned to ship both on Xbox One and PS4, and had to make sure the game would run acceptably on both consoles. Finally, we decided early on to impose some design limitations in order to avoid having to solve some tricky problems. For example, we didn't want to have to deal with AI needing to navigate through portals, especially during combat, so we decided to avoid using them in combat spaces. We did end up having to deal with some AI work for portals, however, as Raz ended up gaining an AI companion as a new power in the game. To reduce performance headaches, we decided to not support portal recursion, meaning the ability to see one portal through another. We also decided to avoid setting up spaces such that 2 portals would ever need to render at the same time, which was mostly successful. In the end, we decided portals were worth a shot, so we began the work of implementing them. At their core, portals need to be able to do 2 things: render the scene from a given perspective, and project that scene onto a surface plane. In Unreal, the former can be done with a scene capture, and the latter can be done by sampling the rendered texture in the material. We decided to implement portals as actors, with a customized scene capture component for capturing the scene onto a static mesh component, which the scene is projected onto. As portals tend to work in pairs, each portal actor stores a reference to another portal, allowing them to be linked together. When talking about pairs of portals, I'll often use the terms entrance and exit to identify them, depending on the context they're being viewed from. Here, we can see a scene that contains two portals, labeled A and B, which are linked together. With the portal actor class in place, the first question quickly arose. How do we decide where to render the scene capture from? For the portal illusion to work properly, the scene capture needs to be placed such that looking into the front of a portal entrance will show the view through the back of its associated exit. The transformation we need, which I'll refer to as the portal transform, allows us to find the equivalent location and rotation of objects on the far side of a portal. Let's look at an overhead view of the scene with a camera placed in front of portal A. To construct the portal transform, we start with the component to world transforms of both our entrance and exit portals. Given the transform of a third object, such as a camera, we start by converting it from world space to the local space of the entrance portal. Next, we modify the local transform to find its equivalent location and rotation relative to the exit portal. This modification can be either thought of as a 180-degree yaw rotation or as a flip over both the XZ and YZ axes. Finally, we convert back to world space via the component to world transform of the exit portal. Here is the scene with the scene captures visible above the portals. Each scene capture inherits the transform of the camera with the portal transform applied so that portal A's scene capture is positioned to see through the back of portal B, and portal B's scene capture is positioned to see through the back of portal A. For reference, here is the function used to apply the portal transform to a location, where entrance and exit are the component to world transforms of the entrance and exit portals. In Psychonauts 2, we decided to not mess around with the scale while going through portals, which is why we opted to use the no-scale variants of the various transformation functions. With the portal transform implemented, the next step was to project this captured scene onto the portal surfaces. Luckily, since the portal transform handles camera placement, the surface material is simple. All it needs to do is sample from the output of the scene capture using the screen UVs. As I toggle back and forth between the camera and portal A's scene capture, you can see how portal A's surface lines up perfectly with the back of portal B. After implementing the portal surface material by sampling the output of the scene capture using screen UVs, portals started to come to life. However, we quickly realized that there were some graphical problems. The most obvious issue occurred whenever the camera moved away from portal surfaces. At first, it was a little confusing, but when looking directly at the output of the scene capture, it became clear. We needed to prevent objects between the back of the portal surface and the scene capture from being rendered. Luckily, Unreal provided a tool just for this task, the Global Clip Plane. The Global Clip Plane is a feature that was added to the engine in order to support Unreal's planar reflections. It works by outputting to the SV clip distance semantic in the mesh vertex shaders, preventing any pixels behind the specified plane from being rasterized. We can specify a clip plane for each portal by taking the position and forward vector of the portal surface, preventing anything behind the portal from being rendered into the capture. One important thing to note is that enabling the global clip plane is not free. According to Epic's documentation, enabling it increases the cost of the base pass by about 15%. With the global clip plane enabled, the scene rendered by the portal's scene capture gets sliced, preventing anything between the scene capture and the portal surface from being rendered. From a distance, things were once again looking pretty good. After getting the basic visuals in place, we decided to tackle actor teleportation next. When we detect that an overlapping actor's location moves from being in front of a portal surface to being behind the surface, we teleport the actor, applying the portal transform to their location and rotation. The important thing to note here is that the order of operations is very important when you have lots of systems involved, such as character movement, player abilities, the camera system, physics, and audio. It's easy to encounter off-by-one-frame bugs, and special care must be given to the teleportation logic to ensure systems don't end up stepping on each other. Actor teleportation gave Raz the ability to run through portals, but our third-person camera needed some help. Our third-person camera determines its final position by starting at a target point, usually RAS, and sweeping backwards until either the desired distance is reached or the sweep bumps into an object, such as a wall. That sweep was unaware of portals, it would go right past them. With debug drawing enabled, you can see that this is happening. The sweep, drawn here in green, ignores the portal surface, breaking the illusion. To allow the camera to move through portals, we updated the sweep to detect when it hits the surface of a portal. We then apply the portal transform to the location and direction of the sweep, which we then use to perform a second sweep on the far side of the portal for the remaining distance. The initial sweep is drawn in blue up until the point where it intersects the entrance portal. The second sweep, which is started at the equivalent location on the exit portal, is drawn here in green. As you can see, with the new sweep logic in place, the camera is able to move through portals independent of RAS, though a few graphical artifacts are apparent as well. Let's talk about how we dealt with those. It may be difficult to see in this video, but temporal anti-aliasing isn't working very well through the portals. Much more visible is the fact that motion blur goes a little haywire on RAS when the camera gets right up against a portal surface. Both issues are caused by the same underlying problem. While the color output of the portal render passes shows up in the main scene, their depth and velocity values are being left behind. You can see here that as far as the depth buffer is concerned, the portal surfaces are solid objects, which explains why motion blur attempts to blur them so heavily when the camera is right up against them. The fact that velocity data is missing also means that temporal anti-aliasing isn't able to properly compute the previous positions of pixels from the last frame, which explains why RAS looked a bit jittery around the edges before. In order to propagate the depth and velocity buffers from the portals to the main scene view, we need to do a few things. First, we need to hold on to references to the depth and velocity textures after the portals are done rendering so that they don't get released to the texture pool. Next, we need to determine for which pixels we want to copy the data from the portal buffers to the main scene. Finally, we need to execute the copy itself. Normally, we could do this by just rendering the portal surface mesh with the depth test enabled and depth rights disabled, then copy our data in a pixel shader, allowing the depth test to control which pixels get copied. Unfortunately, one of the buffers we want to write to is the depth buffer itself, which we can't test against and write to in the same pass. In order to get around that limitation, we can introduce an intermediate step of writing a bit to the stencil buffer for each pixel that passes the depth test in a first pass, then disable the depth test and enable the stencil test for the actual copy operation. The end result is a composited depth and velocity buffer. We execute the portal buffer propagation passes late in the frame, just before post-processing. After enabling the new render passes in-game, the depth buffer can effectively see through the portal. Going back to the default view mode, you can see that motion blur now works as expected when the camera is close to the portal surface. Additionally, temporal anti-aliasing does a much better job as well. The next two issues are easier to observe in actual levels, so we're going to leave this test level for a little bit. As we approach the portal in this fridge, things are looking as expected, but we run into a problem as the camera goes through. Once again, we've got motion blur issues, though from a different source. Across the level, we can see another problem. This area has some fairly thick fog, which likes to flicker as the camera traverses the portal. It turns out both the motion blur and fog issues have the same root cause. Unreal maintains a set of data for each scene view that persists across frames, what they refer to as view state. There are several things stored in the view state, such as the previous frame's view transform, the results of occlusion queries, and various temporal history textures. Since the view state is tied to the view that the scene is rendered from, there is one set of view state for the camera and one for each actively rendered portal. When the camera passes through a portal, most of the useful history information is effectively lost as it stays with the portal that we are no longer looking through. This helps to explain the two issues that occur during camera transitions. To compute motion blur, Unreal calculates the delta of the camera transform from the previous frame to the current one. When the camera goes through a portal, it may end up teleporting quite a large distance in world space, even if from our perspective its motion appears to be smooth and continuous. The farther apart two linked portals are, the more motion blur is introduced during the transition. In order to prevent motion blur from getting out of hand, we do a simple trick. On the frame that the camera goes through a portal, we update the previous frame's view transform in the view state using the portal transform so that it lives in the same effective space as the current frame's view transform. After enabling the modification to the previous frame's view transform, the motion blur issues disappeared. While rendering volumetric fog, Unreal does lookups in the light scattering history texture. When the camera gets teleported during a portal transition, it takes time for that light scattering history to catch up, which explains the fog flicker. To prevent loss of the light scattering history, we can swap ownership of the main scene view's history textures with the portal's history textures. With the previously missing history data now available, the fog flicker disappears. With the view state issue sorted, one last camera-related issue remains. Heading back to the test level, we can see that things break down when the camera crosses through a portal at a glancing angle. If we use the wireframe view mode, we can see that the portal surface mesh is intersecting with the near plane of the camera, letting us see past the back of the portal. One way to prevent the portal surface from intersecting with the camera is to push its vertices away as the camera approaches. This requires the mesh to be densely tessellated. But since we only require the tessellation when the camera is close, we can use LODs to avoid wasting time with vertex shading when we don't need it. With our new vertex shader in place, we can see that the surface mesh is bending around the camera and no longer intersecting it. If we go back to the default view mode, we can see that we finally have a completely smooth camera transition. Now that we're properly handling interactions with the camera, it's time to address what happens when other objects overlap a portal surface. As it currently stands, when viewing an object that is sitting halfway in a portal, we see a clipped version of it due to the global clip plane. For example, this wooden box. This can have some disastrous results, especially when looking at a character. We needed some way to give the illusion that an actor could exist on both sides of a portal at the same time. Our solution was to create a clone of the overlapping actor, which has the visual and collision features of the original without any actual gameplay logic. We use a trigger volume on each portal to listen for when actors approach, then spawn an empty actor that we populate with any necessary meshes, particles, and lights. We update the cloned actor each frame to match their source actor, propagating any changes to their transform, material parameters, and physics state. For skeletal meshes, we also specify the source mesh as a master pose component so that the animation state of the clone remains synchronized as well. One issue with this solution is that we can plainly see the clone walking around the back of the portal, then vanishing into thin air. We only want the clone to be visible when on the front side of the portal surface mesh, not the back. Here's a clearer view of the problem from above. As the rock approaches the bottom portal, you can see its clone appear behind the top portal. As the rock crosses through the portal, it swaps places with its clone, which then disappears from behind the bottom portal. In order to hide the clone when it's behind a portal, we want to be able to clip it, similar to how we used the global clipping plane earlier on. However, in this case, we only want to clip a single actor, not the entire view. To make that possible, we added support for a per-object clip plane by extending Unreal's primitive uniform buffer struct and setting the SV clip distance 1 semantic in the vertex shader. This allowed us to clip both the source actor and the clone against the portal surface plane without affecting any other objects. As a note, outputting to SV clip distance 1 does not add any significant cost to the vertex shaders that are already outputting to SV clip distance due to the global clipping plane. With clones handled, we decided to tackle one last visual improvement. Lighting changes across portals can look pretty harsh. Artists can try to match lighting across portal boundaries, but baked lighting can make that very difficult to achieve perfectly. Given more time on the project, it's possible we could have taught the baked lighting system about portals in order to get consistent static lighting across portal boundaries, but it unfortunately wasn't feasible with our timeline. Still, we wanted to be able to smooth out the visuals along the portal surface, regardless of the lighting setup. Instead of rendering the portal surface as an opaque mesh, we decided to make it translucent instead. This allowed us to perform a depth fade, blending the visuals of the entrance and exit sides of the portal. This does make the surface a little bit more expensive to render, but we found the visual improvements to be well worth the trade-off. Here's what that looks like in action. No more harsh lines. Even with two very different lighting setups, the transition across the portal appears smooth. It's impossible to see at which exact moment objects are teleporting through the portal. One downside of this method is that it breaks down at glancing angles. The good news is, since our game has a third-person camera, it's fairly unlikely that most players will encounter the problem, and it only appears when the camera is within a few degrees of being parallel to the portal surface. With our graphical features implemented, portals were finally hitting our visual target, but they were very expensive to render. Let's talk a bit about the optimization work required to prevent portals from pushing the game past its frame rate budget. The first steps we took were straightforward. Avoid rendering portals whenever possible. Specifically, we could avoid rendering portals scene captures if the camera is either behind the portal surface, the portal is frustum cold, the portal is occluded, or if the camera is far away from the portal surface. Next, we addressed rendering inefficiencies. Portal scene captures spent a lot of time rendering things outside the visible area of the portal surface. As you can see in this video, when the camera is just a modest distance away from a portal surface, most of the scene capture's output isn't used. When rendering the scene capture, the engine performs frustum culling, just as it does when rendering the main camera. But because the scene capture matches the field of view of the main camera, the culling is much more conservative than it needs to be when the portal surface isn't taking up most of the screen. We improved the culling by constructing our own frustum, where the near plane is the portal surface itself, and the side planes are built from the edges of the portal surface bounds and the position of the scene capture. Our frustum is then clipped against the scene capture's view frustum, producing a much stricter result that only covers the area that is visible in the portal surface. With our more conservative frustum culling in place, much less of the scene needs to be rendered by the portal scene capture, saving a good chunk of time both on the render thread due to reduced draw calls and on the GPU due to reduced vertex shading time and less unnecessary overdraw. However, a lot of time is still being wasted shading pixels that the player is never going to see. Once again, we can make use of the portal surface's bounds, this time by projecting them into screen space and using them to specify a scissor rectangle. In practice, this is actually a bit of a pain, as it requires making a bunch of small modifications throughout Unreal's rendering code, as the scissor rectangle gets reset pretty often. There are also some special considerations needed for render passes that do downsampling or can potentially sample outside the region that we're rendering to. For example, the light shaft pass. Additionally, compute passes required their own special attention. We had to make customizations to a number of them, including shaders used for capsule shadows, distance field shadows, and volumetric lighting. With the scissor rectangle set, most of the unnecessary pixel shading work is avoided, though it isn't perfect. Ideally, we would make use of the stencil buffer to restrict the shaded area even further, but that option wasn't feasible for us for two reasons. First, because Unreal makes extensive use of the stencil buffer in various passes, which assume they have full control over all the bits, so we'd either have to modify them all to ignore our specific bit, or we'd have to generate a stencil mask multiple times throughout the frame. Second, while the stencil buffer would allow for tighter bounds, it would not handle the case of a portal surface being partially occluded, as that information wouldn't be known until the main scene view was rendered. Next, let's talk about imposters. We ran into many situations during development where designers wanted to use portals in spaces that could be seen from very far away. We needed a way to stop rendering portals beyond a distance threshold without it being obvious. Initially, our solution was to just fade the surface of the portal to a solid color, but we found it to be too obvious, which limited the distance at which we could get away with it. Next, we tried the approach of fading to a cube map instead. That worked better, but it was difficult to get the cube map to match the intended perspective, and it broke down in motion as well. Finally, we tried applying parallax correction to the cube maps, a technique that is commonly used with image-based lighting, where UVs are computed via ray box intersection tests, which provided to be a significantly more effective solution. Parallax correction provided us with the means of adjusting each cube map to fit the scene, by changing the sizes of the box used to compute the UVs. The effectiveness of this technique varied on the geometry of the scene, and it didn't necessarily work perfectly from all angles, but in general, it allowed us to stop rendering portals much earlier than we previously could. One last optimization technique that really helped us out was dynamic resolution scaling, since most of the portal rendering time is spent doing pixel shading. The currently playing video was recorded on an Xbox Series X with the game running in 120 FPS mode. Thanks to dynamic resolution scaling, performance is maintained even in worst-case scenarios, such as when the player backs the camera through a portal, suddenly requiring the engine to render 2 full-sized scenes instead of just 1. Because portals can cause large instantaneous spikes in GPU workload, we had to spend a bit of time tuning dynamic resolution scaling so that it could respond very quickly, and so that we would have enough performance headroom to be able to take a bit of a hit without immediately dropping frames. Thanks to Epic's fantastic temporal upscaling, even when we have to drop the resolution down as far as 50%, the game still looks pretty good. While many of the problems we needed to solve are graphical, Portals ended up touching a few other aspects of the game as well. Initially, we tried to avoid having to make physics interactions work correctly through portals, but with the number of physically simulated objects in our levels and the ability for the player to use telekinesis, that was a pretty short-lived dream. As a first attempt, I updated the portal clones for physically simulated objects to have collision enabled and to steal half the mass of their source object. I then added logic, which ran every tick that is attempted to keep the transforms in sync. Predictably, this did not work quite as well as I had hoped. We realized that for the clone to be properly joined to its source, we would need to add a custom constraint to the physics engine. We decided to reach out to an external team for help, as no one at Double Fine had any experience writing physics engines. We heard back very quickly and were able to integrate the custom physics constraint. Initially, there were some bugs we had to iron out, such as this fun flip that objects would sometimes do when traversing portals. But after figuring out some quaternion strangeness, we got the portal constraint functional. Because we enjoy a good challenge, Psychonauts 2 not only has portals, but relative gravity as well. Portals ended up being used in a few places with non-standard gravity directions, and they needed to support transitions between areas with different gravity vectors. This test map was created to test both the physics constraint and gravity transitions. A bunch of rocks sit at the top of a tower, which, once released, tumble through a chute, out one portal with a gravity transition, and into another portal with a gravity transition, restarting at the top of the tower. The rocks tumble through this sort of perpetual motion machine, which is pretty fun to watch. Another area that needed some help in order to sell the portal illusion was audio. Psychonauts 2 used Wwise as its audio solution. By default, Wwise has a single listener parented to the camera that all emitters route through. When the camera goes through a portal, the listener teleports with it, which caused a discontinuity in the audio for any spatial sounds playing either around the entrance or the exit, as you can hear in this video. In order to approximate the effect of 3D sounds being able to play through portals, we decided to give each portal the ability to create its own listener, parented to its associated scene capture. As the player approaches a portal, the listener is turned on, with the attenuation determined by the distance from the camera to the portal surface. At the moment the camera goes through a portal, it swaps places with the listener. As Wwise requires that each listener specify the exact emitters that should route through it, we use a volume around the portal to detect any nearby objects that can play sound and add them to the emitter set. For large, distant objects, such as the mail-sorting robot Ford, we also have a manual list of actors to listen to that can be specified per portal. With the portal listener in place, it became possible to hear sounds through portals. finally, let's talk about some other considerations when working with portals. We found it very useful to allow the editor camera to traverse through portals, as it made it much more convenient to tune and adjust portal pairs. The way this is implemented is pretty hacky, as the editor camera works very differently than our in-game camera, but it's not a big deal since the code is only built into the editor and not in the shipping game. Tick ordering is very important and can be the source of annoying off-by-one-frame bugs. One feature that proved especially tricky was our photo mode, as it causes the game to pause, and Unreal does not respect any sort of tick groups or ordering for a paused world. To avoid problematic interactions between portals and the photo camera, our solution was to have the photo camera itself orchestrate some of the portal update logic when in use. Definitely not the cleanest fix, but it got the job done. Finally, when working with portals, it's important to be mindful of floating point precision issues. Some of our worlds were large enough that it started to become a bit of a problem, with different bits of rendering logic disagreeing on whether the camera was in front of or behind a portal surface. In general, it's good practice to do as much of the rendering logic in view space as opposed to world space to prevent accumulation of rounding errors. Thank you.